Probability can be defined in a different way, and to define it, we're going to talk about success and failure. Specifically, successes, which are basically your events, and then failures is all the outcomes that weren't events. So it's just a different way of looking at what a probability is when you just talk about, did I get what I wanted or did I not get what I wanted? Now, outcomes obviously is the sum of these two numbers. So if you take your successes, I'll abbreviate here, and you add on your failures, what you're going to end up with is your outcomes, because it accounts for everything. All right, so we can define probability, which used to be, the probability of an event is equal to the number of events over the number of outcomes. And we can kind of just change it a little bit in terms of these successes and failures. And I'm just going to represent them with S for success and F for failures. So successes plus failures is going to be our outcomes. All right. So with that in mind, if we're talking about our number of events, that's the same thing as successes. So I'll put an S up here. And I'll put a Superman S so it doesn't look like a 5. And then in the denominator, we're talking about the number of outcomes, but this becomes our successes plus our failures. So this is just a different way of looking at what a probability is. Now, when we can break it apart into successes and failures, that leads us into what's called odds. And the odds that we're going to be talking about are the ones that are called against, and these are used for gambling, basically. It can be used in different ways. Now, odds against just means that the failures are going to come first. So it's usually written as a failure number, and then we put a colon, and then successes. So if you were doing odds for instead of odds against, this thing would just flip around and have successes first. But for betting purposes, odds against are how you calculate how much you win if you actually win. So now that we have the pieces defined, the trick becomes, how do I change a probability into an odd? Because we should know how to find probabilities of most things. And I want to be able to change it to an odd so we can start talking about gambling. So let's start off with a simple example. Let's start off with a fractional probability. So let's say the probability of an event is equal to 5 out of 36. Something to do with rolling 2 dice. Okay, so what we need to do is we need to separate these into successes over successes plus failures. So I need to rewrite this. I told you my S's start looking like 5, so I have to be really careful with them. So I know off the bat, right off the bat, that my successes for this event is 5. So my successes is 5. Now I need to break the 36 into successes and failures. Well, I know that my successes plus failures has to equal 36, and I just found that my successes are 5. So this becomes a nice simple linear equation, and most people can do this in their heads. So this 5 here, I'm going to have to subtract from both sides, and I get 31 failures. So when I write this as an odd, you put the word out here, but technically you don't have to. So the odds of this happening are going to be failures compared to successes, and therefore it's going to be 31 to 5. So that would be its odds against, and we're just going to call them from odd. We're going to just call them odds from now on. I did a Google search for the odds of winning a North Carolina scratch-off game, and I picked one of the best odds that were there. Of course, the ticket cost $30, but these are the odds against. They write it differently. They wrote it, the successes then the failures. I guess they're trying to make you think that you're going to succeed instead of writing the failures first. So this is the failures compared to successes. So you have 283 ways of failing, winning a scratch off, and 100 ways of winning something off your scratch off. Now, these are all the prizes. It's not talking about the maximum prize. I don't think they break it down into how many times you're going to win the maximum prize and then how many times you're not going to win the maximum prize. So these could be, you'll win $30, which basically just pays for the ticket, would be considered part of the successes here. So let's go forward. Let's change this into a probability. So I want to change this into a probability. So I want to be able to go back and forth with odds and probability so I can get a good feel one way or the other about this idea. So to make it a probability, we're going to write it as successes divided by successes plus failures. So the probability of winning something off of this scratch off is going to be 100 divided by 100 plus 283. So the probability of this event is going to equal 100 divided by 383. So let's see what that's equal to. 100 divided by 383. And then we want to change it to a percent, so times it by 100. So 26.1% of the time. So the probability of this event actually happening is 26.1% of the time. Really close to about 1 in 4 tickets will win you some kind of money back. It might just be mostly winning back your ticket price of $30. Just how happy would you be if you spent $30 and you got $30 back? It's a positive thing that gets you thinking about, well, gambling more, I guess. In a previous video, we found that the probability of being dealt a blackjack was 4.8%. So what I want to do with that is I want to change it into a odd. So this is how we're going to change percents and or decimals into odds. So the first thing I'm going to do is I'm going to write it in formal percent language, which would be 4.8 out of 100. Now, because of the decimal point in the numerator, I'm going to move the decimal over one spot. So basically that means I'm going to multiply top and bottom by 10. And that way I don't have to work with decimals and I can get back to whole numbers top and bottom. So this becomes 48 out of 1,000. Okay. So if this is 48 out of 1,000, that means my successes, let me come up here, my successes, my S is going to equal 48. So that means my successes plus failures is going to equal the denominator, which is 1,000. And then I can substitute in here 48 for my successes. And then solve for my failures. So I can subtract 48 here, subtract 48 here. And 1,000 minus 50 would be 950, so this would be 952. So my failures are 952. So if I was going to write the odds for getting a blackjack in a casino with one standard deck of cards now, the odds would be failures, 952, compared to successes, which were only 48. And that would be the odds of getting blackjack. Now, it is possible to reduce odds. They are kind of like fractions. This is called a ratio setup. So you can notice that both numbers are even. So one thing we can do is reduce the fractions here, or if we wanted to, we could have reduced the fractions at the very beginning. Either place is perfectly fine. So the common factor between these two, I'm going to guess, is 4. So let's see, 952 divided by 4. Yep, 238. All right. I hope that's enough. So this would be 238, and 4 goes into 48 12 times. Nope, they're both still even. So 2 goes into it. So that means 8 went into both of them. That would be 6. 238 divided by 2 is 119. All right, so this breaks down to 119 and 6. And that's the lowest terms. So it's 119 failures and only 6 successes. All right, so that would be its odds. Now, for gambling purposes, odds are really important because it tells you how much you're going to win. So if we're gambling and we have odds of, let's say, 3 to 2, why not? So this is the odds that a lot of casinos use for blackjack. You win this much money based on odds. So what does this mean? This means if you bet $20, you put $20 down and the dealer sends you an ace and a jack and you have blackjack, how much money are you going to win? Well, to figure out how much you're going to win, just the winnings, your winnings are going to be calculated by taking your bet, this is your bet, and multiplying it by the odds. Let me change my sign here, it looks like a decimal. Multiply by 3 over 2. So you change the odds into a fraction. First number goes in the numerator, second number goes in the denominator. No, this is not a probability. This is still odds. So if we multiply 20 by 3 halves, we're going to end up with, let's see, 2 goes into 20, 10. 10 times 3, we're going to win $30. Now this is just winning. You also get to pull back what you bet, which is the $20, so you don't lose that at all. So you walk away from the table with $30 more than you had, and still the $20 in your pocket. So that's how we figure out what winning is. So this is the odds paid for blackjack in a casino. Now, on the previous page, we found the odds were 119 to 6. So these are the what's called true odds. Let me write that in a different color. The true odds of blackjack are 119 to 6. So under the true odds, if we were going to go looking for our winnings, what we should win if we got blackjack, we would take our $20 and we would multiply it by 119 over 6. Now this one I'm going to have to use my calculator. So $20, 20 times 119 over 6. I'm going to round it up to 397. So this is approximately $397. And this is why casinos make money. It's because they do not pay the true odds. They pay what are called house odds. So this thing over here, this is house odds. They choose on how much they're going to pay out. Therefore, they're actually making a profit where they gave you $30 for winning blackjack on a $20 bet. The true odds is closer to $400 for getting blackjack. So basically, they're raking in $370 above what they really should be bringing in. And this is why gambling at a casino will get you nowhere. Go there with money that you're willing to lose. So in this problem, I have created a game that costs a little bit of money to play, and it pays out for rolling 2 dice. For a sum of 5, they'll get $20. For a sum of 7, they'll win $10. All other rolls lose your $5. So when we do what's called an expected value table, it's really important that you design a table to keep all your numbers kind of straight here. The table is going to be basically what can happen, what is the probability of it happening, and if you can find these two things out, then you can find the expected value of this situation, of these rolling of these two dice. So when I set up a table, what can happen is generally how much money is going to get paid out. Now, there's two different ways of doing this. I'm going to do it in both styles to show you that they end up at the same answer, and you get to determine which style you'd rather do. Both of them are very, simplistic. And one I call take care of the cost at the beginning. The other one we're going to take care of the cost at the end. So this one is going to be cost at the beginning, cost at the start. And if I take care of the cost at the start, then what can happen is a person can play this game if they roll a 7, or I'm sorry, a 5. That's 5 first. If they roll a 5, then they are going to win $20. But if I'm going to take care of the cost at the start, they already paid $5 for this game. So that means when they do win the $20, they're really not getting $20 as winnings. They're only getting 15. Let me change my dollar sign. That was horrible. So actually, if they roll a 5, they win $15. If they roll a 7, their winning amount of money, the money that they'll be given, is $10. But again, they've already paid $5, so they're only going to win $5. And then all others, any other sum that you can come up with two dice that are not a 5 or a 7, they're actually going to lose $5. You're not going to win a darn thing because you paid $5 to play this game. So this is taking care of the cost at the start of the game. All right, so then we have to deal with probabilities. So the probability of rolling a 5, I'm going to come over here to the side. I should be able to fit it in that little box. Dice that add up to a 5 are 1 and 4, 4 and 1, 2 and 3, 3 and 2. And I think that's it. Nope, 6 and 0 doesn't, 5 and 0 doesn't exist. So there are 4 out of, and you have to remember this about dice, it's not 12, it's 36. It's 6 times 6. So this is 4 over 36. And I'm going to leave it in 36 in the denominator just in case I need a common denominator later on. All right, for a 7, that was for a 5. For a 7, you're going to have 6 and 1, 1 and 6. You're going to have 2 and 5, 5 and 2. 4 and 3, and 3 and 4. Remember, you have to reverse them as long as they're not the same number. So that is 6 of them. So this will be 6 out of 36 will have a sum of a 7 showing up. Now, all the others. So basically what we've taken care of is 4 for the 5, 4 different rolls that'll give you a 5, and 6 different rolls that'll give you a 7, for a total of 10 rolls out of 36. So that leaves us 26 rolls out of 36 that will not be a 5 or a 7. That's that kind of that idea of a complement. If it's not these two, you subtract from a whole. All right, so the next step of expected value is really easy. I'll do it in purple. You take the amount of money you can win, and you multiply by its probability. And then you add it on to the next amount of money you could win, and you multiply that one by its probability. And then lastly, it's going to be the amount of money you're going to lose if you don't roll a 5 or a 7, times the probability of you actually losing. And you type this in your calculator any which way you want. Obviously not without the dollar signs. And let's see what we end up with. So 15 times 4, 15 times 4 divided by 36 plus 5 times 6 out of 36 minus 5 times 26 out of 36. So negative 1.11. So it's approximately negative $1.11. So this is what's considered the player's expected value, or the one that actually paid the money for the game or event. So this is the cost at the start, expected type value problem. All right, so let's go the other direction. Same game. If you roll a 5, you get $20. If you roll a 7, you get $10. The game cost $5. So if we do the cost at the end, one thing to notice is my table doesn't require 3 columns. It only requires the winning 2 columns. So if I roll a 5, I'm going to win $20. If I roll a 7, I'm going to win $10. So I'm not worrying about the cost of the game at the start. So I kind of wrote that off to the side because that'll come back into play at the end. Rolling a 5 is still a probability of 4 out of 36. The probability of a 7 is still 6 out of 36. And we're still going to multiply the winnings times the probability. So when we do that, we're going to get 20 times 4 out of 36 plus 10 times 6 out of 36. So let's see here. 20 times 4 out of 36 plus 10 times 6 out of 36. For a grand total of $3.89. So this is not the expected value. And that's where a lot of people get stuck going in this direction. They forget about the cost. So this is the expected winnings of the game, but it's not the expected value of the game. So to find the expected value, you have to take the cost and subtract it from this. So if I subtract 5, we get negative $1.11. So we end up at the exact same answer. Every time a person plays this game, they're going to lose on average. Now this is just on average. They're going to lose $1.11 on average. So if they play a lot of games, like 100 games, they're going to lose $111. They would expect that after doing that. And this is how this determines, for a casino especially, their profit margin. Because they can kind of see if the person is losing $1.11, then they are actually earning $1.11 every time someone plays this game. One little note about this cost at the end. When you do cost at the end calculations for expected value, then the number you end up with, this $3.89, this becomes known as the fair cost. So if the game only costs $3.89 and your expected winnings are 389 cents, then they cancel each other out and you have an expected value of 0. So no one is winning and no one is losing, therefore it's fair. So that's the only thing that cost at the end sometimes comes into play a different role than the cost at the beginning. You can find the fair cost of the game and go from there. All right, I'm going to do a life insurance example. These generally aren't too bad. They just get kind of messy. We're going to do it with cost at the beginning because I think most people understand how a life insurance policy works in that method rather than cost at the end. All right, so basically the same thing's going on here. Let's say a 55-year-old man is going to purchase $250,000 life insurance policy, and the cost of it is going to be $85.75 per month. Given that the probability for this group dying is in a year's time is 0.0027. I did not write it as a percent because that's usually how they're going to write the probability of death rates for insurance companies. So what I want to do is I want to find the expected value of the policy for this man, and then we're going to turn it around and look at how much profit the insurance company is generating with this monthly payment. I looked up all these numbers online, so they're actually quite accurate. All right, let's start off with our table, and there's only two things that can happen in this table. The man is either going to live longer than a year or he's going to die within a year. And that's why I like doing it cost at the beginning, because then you can talk about all the possibilities rather than just the winning. I don't know how a life insurance policy is winning, but the winning policy. All right, so if the person dies, they are going to get paid. Well, they aren't, they're going to be dead. Their family is going to get paid $250,000. But the way you have to think about this is that I kind of think of it as an inheritance thing. I always yell at my mom that she's spending my inheritance. So this $85.75 per month that is coming out of his pocket could have been part of the inheritance to begin with. So technically, that cost of the insurance policy is reducing how much money is really going to the family of the deceased. So the first thing I need to do is I got to figure out how much is this going to cost the man for an entire year. So I need to multiply this by 12. So 85.75 times 12. So we can get the cost for the entire year. So it's $1,029. $1,029. So this $1,029 is not going to be part of the inheritance, so it's really coming off of how much money is coming to the family. They're still getting $250,000. It's just going to be less, $1,029. Now, if Mr. John here, I don't know what his name is, lives, then he's out $1,029. So he's just going to lose $1,029, and he's happy because he lived, not that he lost $1,029. All right. Then the next column, the next row is going to be the probability of living and the probability of dying. Well, the probability of dying is this decimal number. If it was given as a percent, you'd still have to change it into a decimal. But it's already given as a decimal, so I'm going to leave it alone. 0.0027. Then my question becomes, well, what's the probability of him living? Well, if his probability of his dying is 0.0027, then living is its complement, because if you're not dead, then you must be alive. So the probability of my event is 0.0027. Therefore, the probability of my event's complement, i.e. living, is going to equal 1 minus 0.0027. So 1 minus 0.0027 is 9973. So this probability of my complement, my living, is 0.9973. All right, so this probability is going to be 0.9973. So I still have to do the 250,000 minus 1,029. 250,000 minus 1,029 is 248,971. This is equal to 248,971. So that's the amount of money that the family would get if he died, and then this is just how much he's going to lose if he lives. So just like the other expected values, you're going to take how much your winnings are or losings are and multiply by the probability of it actually happening. We're going to get negative 1029 times 0.9973 plus, it's always plus in between unless there's a negative number involved. Let's see here. We got the 248,971, $248,971 times it's 0.0027. So after I type this into my calculator and double check what I typed in just to make sure I don't make a mistake, this turns out to be negative 354. So the expected value would be negative $354 for this man that purchased this insurance policy. But then on the other flip side, the insurance company, on average, if they sell this to a bunch of people, they're going to earn $354 per policy. And this is why they also make lots of money, because they pretty much game the system like a casino will. They make sure that they set the payouts so that they always have a profit. Now, if they sell 100,000 of these policies, so 100,000 policies to 55-year-old men that don't smoke, blah, 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 they're going to earn themselves $354,000. Now, technically, these insurance policies are nice, but for the company, they make a killing on the amount of money they can generate just by saying, we'll give you this money if you die. They make so much more. Even though they're paying out $250,000 for this policy if the guy dies within a year. They just make tons and tons of money off of these policies.